This is section 5.6. And what we're going to do is we're going to look at Euler's formula. And that is their definition 5.6.2. So this is a little out of order, but I think it's just easier to look at the theorems if you have this exponential notation. And so what we have is this identity, e to the I theta, and they're saying they define e to the I theta this way. E to the I theta is cosine theta plus I sine theta. And I don't know, I guess I'm not sure. Somehow, to me, it seems like I've never seen it defined before. It's always been a theorem before. I'll have to look that up. But here's the thing: you know, why does this make sense as a definition? And if you look at Taylor series, then what we know is if I want e to the z, that's 1 plus z squared over 2 plus z cubed over 3 factorial plus z to the 4th over 4 factorial, and so on. If I want cosine of z, that's 1 minus z squared over 2 plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial. If I want, now I'm just using a z, I could use an x or whatever, but just because we'll look at this I theta thing, I thought I'd use a z. And then sine z is z minus z cubed over 3 factorial plus z to the 5th over 5 factorial minus z to the 7th over 7 factorial, and so on. So from those, if I look at e to the I theta, well, that's 1 plus I theta plus I theta squared over 2 plus I theta cubed over 3 plus I theta to the 4th over 4. Oops, left out my factorials there all of a sudden. Okay, so that's e to the I theta. Now, but if I simplify, I have 1 plus I theta. Now, I squared is -1, and so we get minus theta squared over 2. Then I cubed is -1 times I, so that's minus I theta cubed over 3 factorial. And then we're back to a plus 1 with theta to the 4th over 4 factorial, and then it'll cycle between those as we go. So the next one will be an I times theta to the 5th. Okay, so there's e to the I theta. Cosine theta. All right, cosine theta, well, there's no secret there. I mean, that's just what we have there. So that's 1 minus theta squared over 2 plus theta to the 4th over 4 factorial, and then minus theta to the 6th over 6 factorial. So nothing going on there. And then I sine theta. Well, okay, we need our sine theta, so that's up there. So I would get I theta, because I need I times the z, and then minus I times theta cubed over 3 factorial, and then plus I times theta to the 5th over 5 factorial, and so on. Now, notice that when I take these terms and these terms, the cosine and sine terms, add them together, I get 1 plus I theta minus theta squared over 2 minus I theta cubed over 3 factorial plus theta to the 4th over 4 factorial, and it'll keep going on. And they're the same. So we see that e to the I theta is cosine theta plus I sine theta. So, okay, so we have e to the I theta is cosine theta plus I sine theta. So you can define it that way, but using Taylor series, we could also say that that's a theorem, right? That works out that way when we just place these into Taylor series and go from there. And so this, notice e to the I theta then is the angular part of the polar form. And so, you know, I could write z as r cosine theta plus I sine theta like that, but I could also write it in this exponential or polar form. You could still call it a polar form because it's using theta. We got r e to the I theta. Okay, so this is really nice, because then it makes various identities much more obvious as to why they're true. Okay, and we'll look at some of those identities now. We'll go back and look at them, but we're going to use this relationship z equals r e to the I theta to do so. Now notice though, e to the z, okay, e to the z, you have to be a little careful there, because then that's e to the x plus iy, so that's e to the x times e to the iy. And so if I write it that way, notice e to the z, there is your modulus or magnitude, and there is your angle, okay, or you'll see your arg there. Arg z is equal to y in this case. Bad notation. Let me put a z1 there. So z equals e to the z1, then arg z is y in that case, and r, the modulus, okay, or the absolute value of z, is r. Yeah, actually, I guess that's something to also point out with that polar form, right, is that that if I look at the magnitude of z under the polar form, and we didn't do this when we just introduced that polar form and arg z, but the absolute value of z, well, that would be r squared, take the square root here, r squared cosine squared theta plus r squared sine squared theta. And so that's just r, well, actually the absolute value of r, if r could be negative, I guess, then times this square root of cosine squared theta plus sine squared theta. But those are 1, that makes 1, so we just get the absolute value of r. Okay, and we see that, you know, this part, the arg part of the polar form, the stuff involving arg z, that magnitude of that part is just 1. And so we see then under this form, you know, if I write z equals r e to the I theta, then the magnitude of z is just the absolute value of r. Okay, because the absolute value of e to the I theta is 1. Okay, so that gives us e to the I theta. And now we'll go back and look at some of these theorems.